Hello, everybody. Um, I would like to talk about assumptions in this next lecture, which is going to be, I think, the sixth topic that is going to be included in chemical engineering laboratory course. So actually, that was a topic when I was a student. We used to mock about that thing in our chemical engineering courses. Usually, we had a question. We were given a question, then the instructor says, let's make an assumption or a couple of assumptions, and suddenly the question is solved. And we kind of we couldn't get the exact idea behind the concept of assumptions, and we used to mock the idea by just saying absurd thing. Let's assume this, let's assume that, and then the solution magically appears, kind of thing. So I would like to talk about a little bit of about the concept of assumptions, their role in science and in engineering, but it's not going to be hopefully not a philosophical approach, and I'm going to try to relate it to experimental errors, as you are going to see. Actually, I'm going to try to relate it to model errors, how or when you can understand when there is an error in some of your assumptions. So it's going to be a kind of continuation of or continuation from uncertainty analysis. So let me start with this presentation. Role of assumptions in science and their relation to experimental errors. So let's see. Actually, this presentation, so this is my actually the citation for that presentation is partially inspired by the importance of learning to make assumptions by a paper from a paper by Fortus in 2008. For those who are interested, you can go to the original source. It's a quite enjoyable paper. Okay, so actually, it's not the what I'm going to talk about is a meaning or is one of the meanings of the assumption. There are different approaches to what assumptions are, the meaning or how these assumptions are constructed. I'm going to just concentrate on the most pragmatic one for the purpose of our course, I may say. There are other treatments. You are welcome to examine them, to make research on them, but it is going to be just a modest aim of explaining the simplest idea about assumptions. So, to talk about assumptions or the concept of assumptions, I should make a distinction between two kind of problems. The first one are the ill-defined problems in our real life. So what do I mean by ill-defined problems? Maybe to explain what ill-defined problems, it's easier to explain the well-defined problems. Usually exams that we take in high school, in university, most of the questions that we take in midterm exams, in final exams, even in most of the projects, unfortunately, are well-defined problems. What do I mean by that? For instance, this is the stereotype of equation. When somebody says an equation, physics, science, F is equal to ma is the stereotype equation. This is taught in lectures. Then if somebody asks in a midterm exam, m is equal to 2 grams, a is equal to 10 meters per second square, find what f is. This is actually probably a favorite type of student question, except probably the unit, because the one of grams, we don't like that. Then f is going to be what, newtons, whatever. But if you just forget about the concept about the units or the problem about the units, this direct application of that equation is probably the best question, type of questions that usually we like, or students like. Actually, we all like of this question. We just put m and a values inside the equation, then the question is solved. Why is this a very easy question? Why do we like this question? Because there's no degree of freedom in modeling the question. Now, that's an important concept. The question itself, we have to model in our mind how the information in question can be converted into a solution procedure. It is very easy here because everything is very well defined. The equation is given to you. F is equal to m times a. You don't need to think about what m is, essentially what it corresponds to in real life, what a corresponds to in real life. You just multiply those two values, and whatever that f is, it is found very easily. And what is asked is also very, very straightforward. Now you may ask, how else could it be? Actually, it could have been many different ways. What about a question like two metal objects with the same volume but different shapes hit a surface with via free fall from the same height? Which of these two objects will cause a higher damage? Now, this is a much more difficult question because there is almost no information given, no numerical information given here. Nothing about the height of the from which the free fall is executed, and nothing about I don't know, mass of the objects, nothing about the table, whatever. So there is no there's a very high degrees of freedom here that has not been very clearly emphasized or expressed in the question. So therefore, this is an ill-defined question. And for an inexperienced student or an inexperienced person in physics, the next step to solve this question is totally ambiguous. So let's talk about a little bit more detail about the properties of ill-defined questions. Actually, the unknown variable is not always specified. For instance, if I were to any of your instructors ask a question, and in that question, if what is asked is not very clearly emphasized, usual, for instance, find the diameter of a distillation column, typical question, or what is, I don't know, the heat transfer coefficient. Now, these are what is asked is very clearly specified. On the other hand, think about a question like that. Would this, if you just construct such an equipment, would it be profitable? Now, this is actually an ill-defined question because profitability depends on not only economical factors, but also other factors related to things like climate, related to fuel, things like that. So this is a very ill-defined question, but real-life questions are like those. And another interesting point is, and that is something probably you have seen in exams, in some cases, some of you raise your hands during the exam and rightfully say there is some missing information there. Or in some cases, there may be more than sufficient information. But in real life, usually this is the case. Usually we don't know the variables, or actually if you just search for the variables, there is more than that you need. How many of them are you going to include? What about the missing ones? What about the unknown ones? So this is not, the whole picture is not clear. And here I'm going to talk about in a couple of minutes, assumptions may be needed to simplify the problem, maybe to solve the problem. So without those clarifying additional tools, I may say, which may be called assumptions, then we can determine an unknown variable, and we can determine the problem statement clearly. Now, a nice distinction, and it's going to, I think, help you in the courses that you have taken and that you are going to be taking. There may be a distinction between problem and exercise. It's one of those distinctions. So a problem is a task that is difficult for the individual who is trying to solve it. And when I define exercise, I think that explanation will also help you, make you understand what problem is. And exercise can be solved straight away by using a well-practiced procedure. So think about, usually most of the questions that we see in our courses are exercises, whether they are called exercises or not. The unknown is very clearly defined. Usually the procedure is clearly defined. Maybe you're not very well experienced for that procedure, but once you get hold of the equations, once you're experienced with those equations, then it is easy to follow the procedure and come up with a solution, but not that they're exercises. On the other hand, in real life, we have problems. And the difficulty of a problem depends on the person who is trying to solve it. A problem difficult for a student may not be difficult for an experienced engineer. because he has some experience for those ill-defined problems that maybe it's not given in the lectures. It's gained through the life experience, but that may give you an idea about what is taught in school, and also what is required or what is gained in real life experience. Anyway, so let's make a distinction between problems and exercises. So unfortunately, school science is most built about around exercises, such as, for instance, given initialized velocity of a point, determine its trajectory, a very typical question. Or in chemical engineering, flow rates of a hydrocarbon mixture, and the hydrocarbon mixture, all the compositions are very well known, oxygen rate are known, and the reactor temperature are very well known, and determine the outlet composition. The very typical question that probably you have seen numerous times in a couple of courses, starting from mass and energy balances. But there is more. Usually for each of these questions, there is a certain specific set of diagram types that is used. For instance, usually for physics question, a diagram like this, showing given the initial light, a kind of what we call projectile motion, or a typical mass balance question can be solved by this diagram. So usually in lectures, starting from high school, a certain diagram drawing procedure plus some equations are shown to solve specific type of well-defined questions. But in real life, as I said, real life questions are actually, problems are ill-defined. Like, for instance, we don't have real points in real life. We don't have points in real life, but we have objects like planes or helicopters, things like that. And usually there is wind and other accounted effects. And the velocity component, well, here the velocity extraction actually in only one direction in real life, that may not be that much defined. I'm not talking about the details about the second example, about the chemical engineering example. I guess you can talk about all those nuances or all those uncertainties related with real life. So the question boils down to this: how can we solve ill-defined problems, real life problems, using equations and graphical methods we have been taught in lectures? Because actually in real life, nobody will give you, okay, X is equal to this, M is equal to this. They are going to present you a problem. For instance, there's a factory, or there needs to be a factory built, and this is supposed to be the, for instance, amount of product that we need, or maybe in some cases, even that is not going to be, but you need to come up with different types of solutions or alternatives to come up with a feasible solution, I may say. So the bridge between ill-defined real problems and the mathematical well-defined solutions is mostly built using assumptions, we may say. That's where assumptions come into role. One, there, at least what I'm talking about within the scope of this lecture, their role is somehow, or most of their role is somehow convert the ill-defined real-life problems to well-defined lecture type questions or exercises, I may say. So assumptions here in this case refers to less than fully established propositions, which, as I'm going to be explaining in a couple of minutes in more detail, you cannot guarantee that they are fully valid. And that is the nature of assumptions. They are loosely valid scientific correlations or scientific propositions, I may say. But they are going to work if these assumptions are valid. So assumptions usually consist of relationships, relationships which are advantageous to solve a problem. If it's not advantageous to solve a specific problem, then you don't need to make this assumption. It is unnecessary, you don't do it. And these assumptions usually involves equations, principles, things like that. And they are taken for granted for particular purposes, but you cannot prove them, or you cannot show that their validity during derivation, I may say. However, as I'm going to talk about in more detail in a couple of minutes, still you are going to, with scientific reasoning, you are going to, you can distinguish between bad assumptions and good assumptions. But still, if you still think that you continue with good assumptions, there is no way to guarantee that that assumption will work until the very end. So why do we make these assumptions? Because without those assumptions, the solution procedure will be substantially difficult, even maybe impossible for some cases. So you make the assumption, you solve the question, you make it to a well-defined problem, and then you solve the question. Now, once you solve the question, you compare your solution with what you observe. So it's a kind of theoretical result versus experimental result. If they match, then your assumptions seem to be valid. Your models seem to be valid. If they do not match, there may be different reasons because of uncertainty in parameters or things like that, measurement errors. But there is a possibility that there may be something fundamentally wrong in your assumptions. Looking at the relation or the comparison between your assumption, between your results, experimental results, and theoretical results, you should be able to come back and criticize or change some of your assumptions. So that's kind of a feedback approach to converge until a reasonable or a desirable solution is obtained. So let's talk about a couple of examples in chemical engineering. I'll go from very simple examples to a slightly moderately complicated one. So a very simple case, let's say that we have a pump, and this pump takes the surroundings air and pumps it through a pipe into some kind of a reactor. And we would like to find the mass flow rate through this pipe. And we measure the volumetric flow rate, let's say inlet volumetric flow rate of air from the pump to the pipe, and use the equation m dot, which is the mass flow rate, is equal to volumetric flow rate multiplied by density of air. And let's say that here this assume word is involved. Note that this is not an assumption. M is equal to density times volumetric flow rate is actually, you can take it either as a physical law, or even you can take this as a mathematical, just an expression conversion. You can actually define mass flow rate in this case. So I'm not going to go into that philosophical concept of that, which one is physics or mathematics. Still, there is no assumption here, but once you fill this density value here with some value, then this is an assumption. And let's say that you do not measure the density of air online during the process. So you come up with that value, a constant value. Now, first of all, just during this assumption, you should think about, without continuing further, is it reasonable, or why do we make this assumption? Because let's say that I'm going to need this mass flow rate for making an energy balance. So I need mass flow rate value. So I need that density of air value. So it is advantageous to make this assumption, because otherwise it's difficult to solve the problem. So that assumption required. Since I haven't measured the density of air, I have to come up with some value. And let's say that I haven't measured the temperature, I haven't measured the pressure, so I need a reasonable value. So again, why we need an assumption. So let's continue. Still in this case, we are not without help. We can find the sensitivity of density with respect to different parameters. So we may use physical laws to check whether the assumption may be valid around the range that we are running the process. So what I do is, this is similar to what we have done in uncertainty analysis. Since I know physically density of air is a function of temperature and pressure, or from thermodynamics, and since this is, I say, air, and it doesn't change the composition, therefore this density of air is a function of these two variables. Density of air is 1.21 grams per meter cube at 20 Celsius under 1 atmospheric pressure. So I would like to see how density of air changes with respect to temperature and pressure. Now, for 40 Celsius and 5 Celsius, both at 1 atmosphere, it changes from 113 to 1.27, which is actually pretty much small change. So if I think that I believe that the room temperature is about 20 Celsius, which is pretty much realistic, and the reactor also, the inlet and the reactor or the container that the air is pumped into, the temperature is also around this range, from let's say 5 to 20 or to 40. This density 1.21 is a pretty much reasonable assumption. On the other hand, if I check how density changes with respect to pressure, as you can see at 21.1 Celsius, when it's 1.3 bars and 1.7 bars, there is a pretty much drastic change in pressure. Almost, I'm sorry, density. The density, as you can see, almost is doubled. Is pressure is increased by 1.7 times, which means the density of air is pretty much sensitive to pressure. So this may be a weak part of our assumption. Anyway, if there is nothing that we can, if we got no idea about the pressure values in our system, so there is not much we can do. So we should continue. So what we do is we continue with the calculations and then come up with some theoretical results, whatever that we measure at the end. It may be mass flow rate, or we may be using this mass flow rate for other calculations. And then checking with the experimental data, whether experimental data matches with the theoretical results. Now, if they do not match, there may be many reasons. And up to this point in our lectures, we usually refer to uncertainties in measurements. But in some cases, uncertainties in measurements will not cover for the discrepancy between the experimental results and the theoretical results. In this case, you should go back to your model and actually assumptions and check these assumptions. They might be responsible due to the discrepancy or due to the bias. So the whole thing may not be due to random error or measurement noise or bias in measurements, but some assumptions, some bias in our assumptions. So in these cases, then if you think that there is a bias in your system, there's a discrepancy which cannot be explained by uncertainty in measurements or things like that, you go back, for instance, then you think about, you try to come up with a more reasonable value about the pressure values, right? Then you may change this density value, or if there's a drastic pressure difference between inlet and outlet, because as I'm going to explain in the next slide, actually through the pipe, when a fluid, when a gas flows, there's going to be a change in pressure, then a constant density assumption will not be valid. Then actually volumetric flow rate, this is going to be the volumetric flow rate will only be initially valid here. By the way, I haven't talked about very in detail where I have taken this measurement. If you just take it at the beginning of just the beginning of the pipe, then you can find a mass flow rate, and this mass flow rate will be constant through the pipe. So you only need the density of air at the very beginning of the at the entrance of the pipe. But these are just details. I think you get the idea. So you make an assumption, you check all the physical things, and you also come up with where the strength of your assumption lies, and also the weakness of your assumption lies. If you cannot do anything else, continue with the calculations and see whether the results matches with your expectations. If not, the reason of the discrepancy may be due to your assumptions. So actually, you should have realized that this constant density comes from incompressible fluid assumption, but usually we use this assumption for liquids, which seems to be valid for most cases. Yet still, if there are drastic changes in temperature, pressure, still even for liquids, constant density may not be valid. And in many cases, we use atmospheric pressure assumption. Couldn't we have done this? Note that atmospheric pressure assumption requires actually an equipment in which air or liquid or fluid is directly in contact with the atmosphere. So there usually should be a tank with an opening on top. On the other hand, here we have a pump. Actually, I don't know how much you can remember from fluid mechanics course. You are going to much more in detail cover these topics in design course. but what we call a compressor is used to pump a gas, and it is unavoidable that the inlet pressure is going to be pretty much higher, not maybe 1 atmosphere, but probably is going to be much higher than 1 atmosphere. It's going to be much higher compared to the other end of the pipe. So 1 atmosphere, just saying, assume 1 atmosphere is not going to be valid for this question. So at the very beginning, assuming 1 atmosphere is a bad assumption due to physical reasoning. So you should make this a reasonable assumption check at the very beginning. Any absurd assumption is not going to work. So first eliminate your, or just test your assumption using your reasoning. Okay, the second question, find the reaction rate constant. Usually we use steady state assumption. Now, why do we use this steady state assumption? Because it's advantageous, because when it's unsteady state, then we are going to have ordinary differential equations, which are difficult to handle with unknown parameters. So there is a reason why we make this assumption. On the other hand, we cannot prove that some system is a steady state because we do not have a steady state meter. So instead, that what we do is we wait for some time, we measure a couple of variables, and we would like to see after a time they do not change their values, and then we believe that steady state has been reached. But as you have probably experienced in your laboratory, after some time the speed of the response is very, very slow. It converges, but it takes maybe a very much longer time to converge, and that additional value until it reaches, the system reaches to converge, may be really significant. And another problem is, let's say that you waited long enough, the system has reached a kind of steady state, practical steady state, and you start collecting your data, and you take measurements. Unfortunately, during the data measurements for deeming steady state system, or from the system that is deemed to be steady state, that state might be unfortunately perturbed. So there may be small changes in the system or large changes, whatever, still the system may change, whatever the concentration or things like that. So not only to reach steady state, maintaining the steady state is not very easy. So once you do all your calculations, if there's a discrepancy that cannot be explained by a measurement error, that the steady state assumption might be wrong, there might be a dynamic component in your system. So you should also think about that. Now the third and the fourth one are pretty much straightforward. We make Newtonian fluid assumption, which is make mu constant, but make sure that this is only applicable for a couple of fluids that we usually use, and within a reasonable small temperature range. Ideal gas and ideal mixture assumptions are very nice, that lead to also, but in real life they work for a very limited number of cases, yet still they are useful. So whether they are going to be useful or they are valid for your purpose depends again on some experience, some knowledge. But at the end of the day, if you decide that you make this assumption, after you do all the calculations, always check whether there's a discrepancy between your results or not, between your results and your theoretical calculations. And another point is, this is also something I believe important, if you find some unexplained discrepancy, do not simply say that, oh, we have made an assumption, so it should be due to that. You should go back to your assumption and think about this. If you have relaxed this assumption theoretically, if instead of ideal gas, if you have used then if you had van der Waals gas type of equation, would the results, of course the results have probably changed, but would they have changed into the direction which would approach the experimental findings? So you should think about what would change, or whether the direction of the change, would it be favorable, would it be consistent with your experimental findings. So do not say, oh, we made an assumption, so it should be due to this. So be careful about also that. Okay, the last one is going to be about a kind of, I think this is the most enjoyable one. about also modeling and neglecting the velocity at the top of a tank assumption. So this all goes back to Bernoulli's equation. So what is Bernoulli's equation? I have realized that, especially in previous terms, and maybe some of the projects, we should understand in which conditions Bernoulli's equation can be used. Bernoulli's equation, first of all, can be used only for steady state flow, which means that there is no change with respect to velocity, temperature, blah, blah. All the things are constant. It is a constantly flowing system. And another thing is, so this is the first very important thing, there should be no friction. This should be an incompressible fluid. The diameter may change, it doesn't matter. And well, streamline concept, although the formal definitions in streamline, this may be a little bit of difficult concept. I don't know how much we have covered these in fluid dynamics course. There are streak lines, streamlines, under steady state, they are all the same, but when they are not steady state, they are not the same. But very basically, between two cross-sectional areas, we may use this equation. Now, note that here 1 and 2 does not refer to anything related with time, because we are steady state. At steady state, 1 and 2 correspond to two different positions. So here 1 may refer to the entrance and 2 may refer to exit. But as I said, these entrance and exit may be anywhere if you just take a cross section here. Therefore, since we are taking the cross sections here, I'm using these average signs. So this is U1 average, average with respect to radial direction. So here U1 is either you may take this along the streamline, so it's a point here, or U1 average is the average velocity with respect to this radius. So P1 and P2 pressure at these 2 points, and H1 is this distance, H2 is this distance. Again, this is the average distance of this pointer. It's the center of mass here. But for practical purposes, usually we just use this distance of the this height of the pipe. But to be much more exact, this is where Bernoulli equation can be used. Now, how do we use this in a draining tank? So what do I mean by draining tank? The very simple representation, we have a tank initially filled with water. Then there is not a continuous inlet, and there is a hole here. Once we fill the water, let's say that we open this hole, and we let it drain. So we would like to model this system. So the mass balance on this system is simply this, how mass changes in this system. If you just go back, I'm not going to go over all steps, it should be very easy. This simply says that area here, the cross-sectional area here. Oh, by the way, here there's a density constant assumption here. Note that if this is a tank of 100 meters, density here just on the top of the tank and at the very bottom will not be identical to each other. Well, actually for any height, it's not going to be identical to each other. The question is whether that you can make this assumption that constant mass can continue, whether it's going to take results or not. But for the sake of this question, since we are talking about small heights, density constant is a reasonable assumption. So they are cancelled, and area times dH over dt, the rate of change of this height, is equal to minus area here, this small area, multiplied by U2 average. U2 is the average exit velocity with respect to this opening. And an initial amount of water is here. Now, area is measured here. The small area is measured here. H is given an initial value. What we need to solve this question is to find this U2 value. However, please note that this is not going to be constant. So what is it going to be equal to? Actually, we have an energy balance. We can make an energy balance here. And here, as you can see, this is an unsteady state mass balance. And unsteady state energy balance is not that much straightforward. Instead of that, what we do in our courses, in a couple of courses, and probably in chemical engineering laboratory course, for those who have conducted this experiment, what we do is we make the assumption of pseudo steady state. And in pseudo states, and also no friction. And well, the nature of this assumption is not that much straightforward, but basically it says that pressure is equilibrated instantly. So you just think about just the dynamics of pressure is totally neglected. So in this case, Bernoulli equation can be used from between surfaces 1 and 2. 1 is surface here, 2 is exit. Now note that probably, or maybe not, some of you just didn't think about that in that much detail. You just directly, automatically use this equation. It shouldn't be that much automatically, because actually, in order to use Bernoulli here, there should be a flow, a constant flow like this from this region and this region, right? And this flow is going to be also going here, and the height should be the same. Height shouldn't change because everything should be identical. I'm sorry, it should be at steady state. So inlet flow rate here, there should be an inlet flow rate which continuously comes into the tank, and there should be an outlet, and these two match each other, and there should be a constant height here. In this case, remember the Bernoulli equation, it's like a flow, a continuous flow in a pipe. So there's going to be a flow from this point here to this point there, and we should be able to write that Bernoulli equation between those 2 points. Unfortunately here, this height is falling down, yet still we are using Bernoulli equation. And how do we do that? Actually, we neglect the dynamics of pressure. Therefore, actually pressure is at each point during this height decrease, pressure is in no time in this system equilibrated. And in this case, we may be using the Bernoulli equation. One very big assumption. In some cases, this may not be valid. For instance, there may be a very fast decrease, or there may be a very large turbulence, things like that. So one needs to check this assumption. So here is actually, this says that if you just take this bottom point as h is equal to 0, here there's this going to be h is equal to 0. So there's going to be h component here which changes with respect to time. There's going to be an inlet pressure, atmosphere, outlet pressure of atmosphere. They're going to be canceled. We are going to need this velocity here at this point and this velocity at the outlet. Now, actually, there's a dilemma here, as I said. Although we assume steady state, but we say that at the same time, u here and h are functions of time. Yet still, we continue, right? The second one is even more kind of problematic. We are going to take u1 to be equal to 0. This surface, or very close to 0, but practically it's going to be 0. Surface velocity is equal to 0. And this is a strange assumption because actually u1 is the velocity of the water level in the tank. Actually, it is dH over dt. This is actually the definition of u1. And note that we have already modeled as this dH over dt here. So if you take u1 to be equal to 0 here, actually put it here, then u2 is going to be also equal to 0. So these assumptions are pretty much interesting. We just assume u1 to be equal to 0 only in Bernoulli equation. And why do we do that? Because since this area here, cross-section area, is much, much greater than the exit area, then in this equation, we expect that this u2 is going to be much larger than u1. Then you can safely neglect the contribution of this u1 here, but not in this equation. Note that again, dH over dt is u1. We don't neglect u1 here, but here we neglect it. So maybe this may give you an additional idea about the nature of assumptions. There may be contradictory in some cases, but mathematically, this very much helps the situation, and it's also pretty much realistic assumption mathematically. So within the scope of this equation, when we use this, you can safely remove u1. And when we do that, Bernoulli equation leads to u2 is going to be equal to some function of square root of h. So And what we are going to do is, since we have an expression for U2 here, we just put this U2 in the mass balance equation, and we come up with the rate of change of liquid level in our tank. As you can see, dH over dt is going to be equal to 2 measured areas and a gravity. So this whole thing is going to be constant, and h to the power 1 here. With an initial liquid height or water height, this system can be solved. Let's say that we have solved the system, and this black line is a theoretical solution. And when we do the experiment, these dots are obtained. As you can see, they pretty much do not match. So what we do, the first thing that we can do is, maybe we have measured these areas, probably gravity, uncertainty gravity is pretty much negligible. We measured these areas, there's going to be probably some measurement error, uncertainty. And I have exited, of course, this is an hypothetical situation, but assuming that I have made a 100% uncertainty in area values, I come up with these solutions, these two solutions. So I just increase this value that I found by 100%, and I decrease it 100%, and I solve this system again, dH over dt, using MATLAB, and I obtain these two solutions. So the question here is that we would like to answer is whether this discrepancy may be due to an uncertainty in measurements because of some measurement error, or is there something else? So I draw these two theoretical responses. There's one important thing that I should mention here. Now, a lower coefficient value here might also mean, right, there may be also some frictional forces, because here I assume that there is no friction, but one way to handle friction, for those who remember from fluid mechanics course, is to include, especially since there's a valve opening here, to add an additional constant here, somewhere here, something like alpha. So velocity is going to be some proportion of this value. Therefore, this whole value will be decreased. So when this whole value will be decreased, then due to friction, draining will be slower. So maybe this is those dashed lines might refer to both uncertainty and also some maybe an additional frictional component. On the other hand, what I observe is this. Therefore, what I can say is, first, it doesn't match the expected response. When I add, even if I add some friction here, still it's very much far away. What about this point? Well, it seems to match. Unfortunately, still it doesn't seem to match, because the initial response is faster in reality, but then it gets slower. So if I were to obtain those results, I would say that the character of my experimental response does not seem to fit to the theoretical calculations. So I would say that the observed bias between the experimental values and the theoretical values may be due to the model and simplifying assumptions. It may be possible that the initial phase is faster. Maybe this is not square root here, then it is slower. So there is an actually, as the liquid amount in the tank is reduced, then the speed of the level in the tank is slower and slower. Maybe it is possible that, let me go back to this part here, maybe the tank level, when it is here, the tank level here and the speed of the outlet flow, maybe we should be including also this u value here, or maybe it's vice versa. Maybe we should include, we shouldn't say that simply u1 is equal to 0 at the very beginning. I don't know about that. These are just the values I come up with. They are not based on very strict analysis, but as I said, there may be something wrong with some of the equations, and the usual suspects for this case are those two assumptions. Maybe this pseudo state I find it less being of a suspect, but more of a suspect of this one, but one should check about this. So the moral of the story, there is a concept called model error, usually due to those assumptions. So take home message from now on in, I don't know how many experiments, if or how we are going to be conducting our experiments, but later, whenever we start conducting again, once you come up with the results and check the uncertainties or things like that, you should realize that there may be also a model error component, which possibly comes from assumptions. You should always, once you make the assumptions, always think about those assumptions may not be valid. So you can, there is always a possibility that it might be distorting your results. So keep that in mind. Okay, thank you. That's the end of this talk. I hope to see you, or not see you, but you see me in another lecture. Okay, bye.